So this lecture is going to be more focused on Ohm's law. Voltage equals current times resistance. So we're going to look at what current is, what voltage is, and what resistance is. V is voltage, I is current, and R is resistance. And we can put them together and simply state that voltage equals current times resistance. Before we get there, let's review electrostatics. Electrostatics involves charges on an object as static, meaning it is not moving or flowing. So electrostatics, we can apply Coulomb's law of two charges can exert forces at some distance. But these are unmoving charges. So we can say an object can have either a positive or a negative charge. We know that like charges repel and opposites attract. That a force is created between the charges. And this is what we call Coulomb's law. So we looked at polarization where the negatively charged balloon repelled the electrons in the wall, yet stuck to the slightly temporarily positively charged surface. So we can apply Coulomb's law a couple different ways to polarization. We also learned that there are three ways that we can charge an object. Can you name them? So you can pause this, try to think of them, but I'm going to go over them in a second. The first one was that we charge by friction. We rub a balloon on our shirt. We know that the triboelectric series that some objects are more likely to give electrons, some objects are more likely to gain electrons. So we can charge by friction. We can also charge by contact. If we touch an object, we were able to touch the aluminum piece that was hanging from the string, so we can charge by contact. And third, we can also charge by induction. So when we place the balloon close to the electroscope, we could touch the electroscope and remove some of the electrons, and the leaves stayed repelled because they had a net positive charge. So what is electric current? Well, current is the movement of electric charge, or the flow of charge. Remember, electrostatics, they were stationary. But current, we're going to start moving those charges. Current flows when free-flowing electrons move. And we'll be comparing conductors versus insulators. And current, which is the symbol I, is measured in amperes, or amps, and we'll just call it capital A. So which way does current flow? Well, Benjamin Franklin developed the idea of electric current, and first used the term to describe as positive and negative to describe the charge. But we define current as flowing from positive to negative, right? From cathode to anode, even though the direction in which electrons move in the circuit is actually from negative to positive. So make sure you add that in your notes. Current, we're going to be saying, moves from cathode to anode, whereas electrons actually move from anode to cathode. Make sure you get that in your notes. So why does current flow? Well, electric current only flows when there's a difference in energy between 2 points in a circuit. We're going to call this the chemical potential difference. So just as water flows downhill from high gravitational potential to low gravitational potential energy, so does current. Current flows from high electrical potential to a low electrical potential. So they're kind of the same concept, we're just applying them to different forms. Current is deadly. Current is what kills. That you could feel what we would consider a small amount of current at 0.001. We can feel this. And pain would be at about 0.005 amperes. And then you could get some muscle spasms at 0.01. And you could lose muscle control at 0.015 amps. And if it's through the heart, 0.07 can cause a serious disruption, even possibly fatal. So current is what does damage. So let's look at this slide. So here we can say that current in the outlet is able to be pushed through you, doing damage to your own electric circuitry. Your body is run by a series of electrochemical impulses. So if you handled a wet hair dryer, it would be like sticking your fingers into a live socket. Very, very dangerous. But why can a bird stand on wires and not get fried, or a squirrel? Well, there's no electrical potential. There's no difference while the bird's feet is on the wire. Therefore, it cannot push current through the bird. So the bird can stand here on the wire of high potential, but it better not touch the neighboring wire. Better not touch something else, because it gives it somewhere to go, and that would be traveling through you, or the bird itself. So what is voltage, right? We talk about batteries. Batteries provide voltage. Well, voltage measures the difference in the electrical potential between 2 points in a circuit. Think of this like a height measuring the difference in gravitational potential energy. That voltage, or electrical potential energy, is measured in volts, which we'll call V. A difference in voltage is required for current to flow. It means that there is energy to do work. So we can create a difference in voltage, and a battery uses chemical energy to create a voltage difference between its two terminals. So we can get a voltage difference, a chemical potential difference from here, from the cathode to the anode. And as a result, these little bodies here are transporting energy to the bulb. and we get heat and light energy. So we get this chemical energy of these charges that are moving through here, and we get electric current. So once they deliver it, they come back and kind of refill up, and they keep this electric circuit going. So here's a better depiction of what voltage is. So if there's no height difference, there's no water flowing. So this is just a tube with water in it. If there's no voltage, there's no charges that are flowing. But as soon as I lift this off the ground, you can see that water is going to flow, right? The height causes the water to flow. Well, so does the battery. The battery allows for the chemical difference, so the chemical potential difference. And this is what allows for current to flow. You have a positive terminal and negative terminal. These have different potentials. So the height here causes water to flow in a pipe, where current flows in a circuit because the battery creates a voltage difference. So here's an interesting way of kind of looking at this. Were physicists wrong in determining where current flows? If electrons flow from anode to cathode, is this correct? Well, it's kind of just an incomplete picture. So the picture to the left indicates that current flows from the cathode to the anode, right? Here, current. But what's wrong and what's right? When current was first named, it was in the mid-1800s, 50 years prior to understanding the electron. And electrons move from anode to cathode. And that is correct. And we'll talk about this analogy of spokes in a car. So we'll go with this version here, which is called the conventional diagram. But really, the modern electron flow is actually correct. The conventional flow says that electric charges move from positive side to the negative side, where the electron flow notation, which is the modern view, shows that electric charge actually moves from the negative side of the battery to the positive side. So we'll just say, from now on moving forward, we'll say, we're going to go with this. This is kind of the conventional way of saying current flows from cathode to anode. But a better view is saying that electrons flow from the anode to the cathode. So moving on. So what is resistance? Well, resistance is a measure of how strongly a wire or other objects resist current flowing through it. Resistance, R, is measured in ohms, and we'll use this symbol here, omega. So think of the relationship between resistance and the current like water flowing from a bottle, and the relationship is inverse. So when we apply Ohm's law, voltage equals current times resistance. If I double the resistance, one has half the current. So let's look at this with a picture. If I only have this little opening, I'm not going to have a whole lot of water flowing out of here. If I open this, right, if I decrease the resistance, I'm going to have a lot more water flowing. This is going to have a lot more current because it has less resistance to holding that water in the container. So less resistance, more current. So let's apply current and resistance to the actual circuits that we created. That 1 volt, single resistance, has full current. That if I add a second bulb, if I double the number of light bulbs, I've doubled the resistance. Twice the resistance has half the current. And I'll view this as being dimmer. And if I have 3 bulbs, I'll have 3 times the resistance. I'll only have 1/3 of the current. And I can see this visually because it's going to be dimmer. So the brightness of a bulb provides a visual cue as to the current flowing. If the light is on, the circuit is closed and current is flowing. When the bulb is bright, the current is high. When the bulb is dim, the current is low. So there's certain materials that allow for current to flow through them, and we call them conductors. Conductors, and generally they're metals. Current passes very easily through these materials. Electrons flow freely, and they have a very low resistance. And these metals include copper. Those are primarily the wires we use, are copper, a little aluminum. Gold is a very good very good conductor, and silver. But then there's also semiconductors. They have some resistance. In silicon, these are used in computer chips. This would be considered a semiconductor. But materials that do not allow current to flow through them are insulators. Current does not easily pass through these materials. They block the flow of current. Electrons do not flow freely through an insulator, and these have a very high resistance. An example would be rubber, glass, or wood. So when we look at a wire actually has a metallic conductor inside of it, but an insulator, generally rubber or plastic, on the outside, that's your insulator. So we can touch the wire and not have any damage to us. But if we touch the live wire itself with current flowing, we could be shocked or burned or injured, actually somewhat severely. So conductors, the metals within the wire, are actually covered with an insulator that inhibits the flow of electrons, so we can touch the wire safely. So when comparing conductors to insulators, we would say that, so for a moving electron, electrical current is made of moving electrons. That atoms stay fixed in place. It's only the electrons that are moving. That the atoms in an insulator, they're actually bound. The electrons are bound to them. that in an insulator, electrons are tightly bound to the atoms and cannot move. But an atom and a conductor, they move very readily. In a conductor, some electrons come free and can move to create the electric current. And since electrons are negative, they move in a direction opposite of the current. So, some resistance of common objects. The resistance of objects varies. Electrical devices are designed with a resistance that causes the right amount of current to flow when the device is connected to the proper voltage. So dry skin has a resistance of about 100,000 ohms, very, very high resistance. But wet skin has much lower resistance. Therefore, the same voltage will cause more current to pass through your body. That's why when you're wet, you're just more likely to be shocked or injured. Electric current can flow more readily because it has a lower resistance.